In the previous lecture, we saw what is two beam interference by amplitude division. Okay. So, we saw two beams of light which will overlap in space and time and will give you a fringe pattern. And what exactly that fringe pattern looks like, and then we derived mathematically also by the superposition principle, what will the fringe pattern look like, and how it depends on the phase difference between these two beams or these two waves. Okay. So, here I will tell you what exactly is meant by amplitude division experimentally. I already told you that amplitude division means each of the two waves have almost equal, nearly equal, or the amplitude is divided. Okay. And it can be a equal division or it can be an unequal division. Both will give rise to interference fringes, and the difference between these two kind of fringes. Now, let me see how to get this amplitude division. Okay. So, the amplitude division is brought about in a Michelson's interferometer. Try to recollect some of my first few lectures where I was talking about the properties of lasers, and I had described to you the Michelson's interferometer. It is a very important interferometer. It can be set as an example for different topics which are somewhat related to the interference itself. You will realize at the end of this lecture the connection between what I spoke about then, one property of laser then, and the interference pattern. If in case there was some doubts in your mind regarding some of the properties of lasers, then it will definitely get cleared here. Okay, so let us get along with the Michelson's interferometer. I will just describe to you fast once again, you already know. So, this is one mirror, A2 represents one mirror and A1 is another mirror. This is a source of light, okay, and this is at 45-degree angle plate. That means it is partially transparent and partially reflecting. Okay. So, some part of this light which is coming from this this source falls onto this and gets reflected and goes to this mirror A2, and some part of the light goes here. Okay. So, there is an intensity division. For the moment, think the division is equal. That means the intensity that goes here and the intensity that goes here is equal. There is no dispute about that. Okay. So, that means this plate you are able to. So, I have one wave coming in here, one wave is going here, one wave is going there. Okay. So, these two waves have been divided in amplitude. That is what I mean by amplitude division. This wave has come here and the amplitude gets divided because part of that beam comes here and part of that beam goes here. For the moment, we will take it as 50-50%. 50% comes here, 50% goes here. So, the amplitude of that wave has been divided and nothing else. So, a wave is associated with amplitude and phase front also. Okay, since I will be talking so much about phase. So, nothing has happened to the phase. It is exactly as it is before for both the beams of light. But the phase front has not changed. Okay. The phase front has not changed, we have only divided the amplitude. Okay, now what happens to this beam? So, you have one beam of light going here, it will come back, going here and it will come back, and this mirror, and part of it will come here, and some part of this beam which is coming back will pass through this plate and will come here. So, you have one set of beam which is coming this way and one set of beam which is coming from there, and you see it on a detector, any kind of whatever detector, can be anything, which will detect that light, which will detect that intensity of light here. Okay. Now, out of these two mirrors, one of the mirror is movable. Say I'll allow A2 to be movable and A1 is fixed. And this L2 is the arm length of this, that means from here to here. And L1 is the arm length of this, from here to here. Okay. So, if I feel like I can move this and change the difference L1 minus L2. If I do not feel like, I just leave it as it is. So, I will feel like if I want to see a certain kind of fringe, I will try to do that experiments by moving this up and down. So, I only have this movement parameter available to me. Okay. And if I move this and I will try to see, am I getting some fringes here? Am I getting a dark spot? Am I getting a bright spot here? That is what I will do. So, it is exactly like what I have said in the previous lecture, only the phase is changing, nothing else is changing, and you have divided the amplitude. And the light is monochromatic. That means omega has remained the same as before. Omega for both the beams is the same. Okay, the frequency is the same. Okay. Now what will happen? Now what will happen? Basically, I am trying to recreate the previous lectures, the derivation by actual experiment in the Michelson's interferometer. So, here I have said the length of the arm is L1 and L2. Okay, this is L1 and L2. Path difference between this and this will obviously be L1 minus L2 and twice that, because okay, it is going here, coming back, going here and coming back. So, twice of this arm length. L2 is the arm length of this, but the beam is going up and then coming down. So, it becomes twice L2, the beam travels this twice L2 path. So, the path difference is this. Then the phase difference is obviously 2 pi delta by lambda. Delta is a path difference, small delta is 2 pi delta by lambda is equal to k lambda. K is the wave vector, you know. Okay. K delta. Delta, this is capital delta, this is small delta, this is capital delta, small delta. So, this is the phase difference. I am bothered about the phase difference because my intensity depends on this phase difference. Okay. So, if I take the case 1 only, I is equal to I0 into 1 plus cos delta. I have just written this equation back there, so that it is right in front of me. Okay. So, from this phase, I want to make some judgment about the intensity that is that this detector is seeing. So, depending on the changes in delta, I will get this the changes in I, exactly as I have described before. So, that is what this detector will detect. Now, the thing is, I must look at a slightly generalized case. Now, in this case, the generalized case is this source of light here may be slightly of an expanding source. You know, it may not be exactly a pencil thin line. Okay. I am doing everything with just normal light. I have not still come across, said anything about using laser light. Okay. So, this source can be a slightly diverging beam. Okay. So, some of the rays will hit this beam splitter at an angle, and so there will be an angle on this mirror too, and similarly here. Just because this source of light is not perfectly perfect with this axis, the S0, 0 axis. It is not perfect with that. It comes at an angle. So, let us see what will happen when it comes at an angle, what will happen here. So, to represent the Michelson's interferometer, okay, in a different way, you have to just imagine this detector I have placed here. What is the detector looking at? The detector is actually, this has a spot size, maybe as big as this. So, the detector is looking at this mirror and is looking at this mirror, this detector, through this and then through this. So, it is looking at the source image on this mirror and on this mirror. Okay, this detector can see the image on this mirror and on this mirror. So, that can be represented in the following way. So, here these two mirrors, I have just put it as A1 dash and A2 dash. It is actually this A2 and A1 here, and the source here is here. Okay. So, where will the image be of this source be formed? From the first mirror, if you take the virtual image, it is formed here. Let me call that S0 dash. And let me call this S1 dash. Okay. So, what is the detector seeing? The detector is actually, this detector is actually seeing an image here and the image here. That means it is seeing the image on this mirror A1 and on this A2. So, actually if you put it this way, this is the source S0 and these are the two images because of those two mirrors. So, it is coming here, coming to this and getting reflected, and this one is coming here, right up to here to this mirror and then getting reflected. So, you are getting these two rays onto this detector. Okay. So, and if you, it is a virtual image obviously, so you see one virtual image here and one virtual image here. Okay. So, this is one way the detector is looking, one way of representing the way the detector is looking at the source. Now, see, this is at an angle of theta. This is impinging at an angle theta. So, this is theta and this is also theta. Okay. The distance between A1 and A2 is suppose I write it as D is equal to that L1 minus L2, which is from here L1 minus L2. Okay. I call it D, I just call it D. But then it is making twice the transit. So, the distance between these two images S1 dash and S0 dash will be 2D. Okay. So, this is distance between S1 dash and S0 dash will be equal to 2D. Okay. So, what will be the path difference? Okay, path difference will be from this image, the path difference will be this. Okay, I'll call the path difference as delta. Delta, suppose this will be 2d cos theta. Okay, this path difference. Okay. Then what will be the phase difference? Once you have the path difference, you can always ask for a phase difference. So you have phase difference, which is small delta, capital delta is path difference. Okay. And then you have the small delta. Small delta is the phase difference, will be wave vector k into delta. That means 2 pi by lambda, which is k, into 2d cos theta. Okay, so that would be, now when will you get maximum intensity? You will get maximum intensity, as we've seen before, when delta is equal to twice pi m. You will get the maximum intensity. M is some integer, 0, 1, 2, 3, etc. is equal to m. So from all these equations you can see 2 pi delta by lambda is equal to twice pi m. Do a bit of jugglery, 2d cos theta is equal to m lambda. This is the equation I am looking for. Okay. This is you are just sort of juggling some, doing a bit of algebra, going from this side to this side. Okay. And this is 2d cos theta is equal to m lambda. Doesn't this look very familiar to you? Try to recollect the lectures on grating equation. Okay, this looks a lot like the grating equation. Okay, and it has got similar implications also. Okay. So here what will happen is, so I have got 2d cos theta is equal to m lambda. Why do I bring this in? I bring this in because my source is at an angle. It is not exactly parallel like this. It is at an angle theta with respect to the axis of the Michelson's interferometer. So this is a more realistic form of the interference pattern. Okay, because any source will have some finite width and it will be spreading out. So what will I see at the detector? At the detector, actually I will see some ring pattern like this. Dark and bright fringes, dark and bright fringes. Okay. So this is what you expect to see here, and you will see that for any ordinary source. Okay. It's very much like this, where remember in the grating equation m was called the order, first order, second order, third order, like that. Even here m is called the order, and it takes values of 1, 2, 3, 4. Okay. So this is the order, and theta gives you this angle. To what extent this angle can go till this formula is valid. That is actually theta should be not very far away from pi by 2. So, it should not be very far away from pi by 2. But okay, you have this divergence. If you have two diverging a beam, then you are not going to see anything. Okay. But on that, depending on the angle at which the ray hits these mirrors, you will see different kinds of patterns like this, these interference patterns, dark and light rings. Okay. So, what have I done? I have my initial two beams have been amplitude divided actually in practical experiment, and I have got interference fringes from them, okay, depending on the path length between the two mirrors, because the path length translates into phase difference. Okay. So, actually in a Michelson's interferometer, what I had told you before was that that this path difference, it can you can move it up and down, and at a certain length, if it goes too far away, if L2 is very much far away from L1, that means your D distance becomes very large, then you are not going to get any interference pattern. Okay, that is what I had told you in those first few lectures when I described the coherence length and coherence time of a laser. I'll come to that also. Okay. So, what I want to say is that if you have an ordinary source, any source, and it is monochromatic, then you will definitely get this fringe pattern. Okay. But ordinary sources are not always monochromatic. Are they monochromatic? No. So, you have to make them monochromatic. That means, out of all these wavelengths in that source S0, you have to select only one, and then only you can make such a interference pattern happen. So, there are certain light sources, maybe a sodium lamp, which gives only one frequency or close to one frequency. Only with that you will be able to see a pattern. But that is not true about laser. Laser is almost monochromatic. I say almost because it is not absolutely a delta function. If you remember, we had discussed that. It is not a delta function like this. It has a little bit of a width. But I can say, as compared to ordinary light, laser light is monochromatic. So, in place of this source, if I had placed a laser light, I will get these fringes very easily. You do not have to do much. And even if I use two different sources instead of one which is getting divided, I will still get an interference pattern. So, that is the property of the laser light, okay, which gives you an interference pattern easily. And if you use a laser light, you can move this quite roughly. I mean, not with too much of care, you will still get an interference pattern. Okay. So, let me relate the coherence length that I spoke of, coherence length and the coherence time, which I had spoken of before. It is related to the blurring of interference pattern. So, in case of the blurring of interference pattern, what do I want to say? The interference pattern gets blurred, which I have shown you. Basically, you have these lines, fringe lines, and they are not clear cut. They are not clearly separated from, they are separated, but you cannot see them visually or through a detector. There is a lot of a fuzziness about it. Okay? That fuzziness is called blurring. The blurring is caused by finite coherence time and length of the light emitted by the source. The interfering waves with a path difference are represented by sinusoidal segments displaced by each other in space and in time. So, this is the wave. This is another wave, another bit of wave, and this is another wave. Notice they have the same frequency. Okay. So, now you will get an interference pattern only in this region between this point B and between point C. Okay. So, you will get it only during this time when these two waves have a phase relation between them. Okay. So, you are not going to get it before that. All right. So, here I say interference rings of different diameters, rings because it was that Michelson's interferometer, are formed in the Michelson's interferometer due to different frequencies of a non-monochromatic wave. So, if I have a monochromatic wave, I won't get these rings. If I have, I will get fringe pattern, no doubt, but if I have a non-monochromatic wave, again I will get those fringe pattern, that means those rings. I should not show the fringes this way, I will show it as rings. Okay. So, I will get them as rings like this, but these rings will correspond to different wavelengths. Okay. The maxima and the minima of the interference pattern of waves of different wavelengths are displaced, and therefore, interference pattern is blurred. Okay. In the direction of angle theta, the path difference in the incident ray is equal to the coherence length. Okay, this I bring in the coherence length. 2d cos theta is equal to the coherence length, and tau c is the coherence time, c is the velocity of light. So, tau c is the coherence time. And tau c is So, what I want to say in this case is, remember I had told you when I was trying to describe what is coherence time and coherence length, which is a property, coherence time, property of a laser, that it has very long coherence length, it has long coherence time. So, that time I had said, so in case of a laser, this thing, when these two are sort of well related to each other, is very long in case of a laser light, but not so long in case of a ordinary light. So, if this is very short, your 2d cos theta will also become short, okay, will be small, and your coherence length is short. So, you won't really get an interference pattern. You won't get a good interference pattern. You will get a blurring of the interference pattern. So, the coherence length, which I was describing before, and then I connected the coherence length with a Michelson's interferometer experiment. So, the coherence length and the coherence time seems like an abstract idea, but you see the consequence of the coherence length and coherence time in your fringe pattern or the circular fringes. Okay. So, the interference fringes in general gives you an idea of the phase of a wave or the phase difference between a wave, and that is the useful part. So, in any picture, can you record or capture the phase? The way you can do it is through an interference pattern. The moment you have a fixed interference pattern, be sure that you can back calculate and always know what is the phase difference. So, for any picture, to get a phase information is very important, and that is there in any interference pattern. That's the importance of interference pattern. That's the importance of getting a not so blurred interference pattern, but a sharp interference pattern. So, today we have seen, in the last two lectures actually we finally see that this blurring will come one because of non-monochromaticity, and two, it will come because the amplitudes are not equal. The two waves amplitudes are not equal, and also 2, 3 because of coherence length or coherence time, the relationship of coherence length, coherence time with the wave. Okay. So, these are the three things which gives you a blurring of interference pattern. Okay. These are the conditions which have to be met, the proper conditions, in order to get a sharp interference pattern. Okay. And the interference pattern gives you an idea of the phase or the phase difference between two waves. Okay. We will go on further and see how in my next few lectures where else interference becomes important and what other kind of interference is possible.